de physique mathématique et de physique subatomique à l'université Constantine 1 sous la direction du professeur Habib Aïssaoui. Le jury est composé de M. Habib Aïssaoui, directeur de cette thèse, les examinateurs M. Boussaïd Mounir, professeur à l'université de Msila, M. Samir Mistalji, maître de conf à l'université, à l'ENS de Skikda, Madame Monia Habad, maître de conf à l'université Constantine 1, et Monsieur Mohamed Farouk Riti, maître de conf à l'ENS de Constantine. Donc, Monsieur Khmachmiya, vous avez la parole pour votre exposé et merci de respecter la durée de 30 à 40 minutes maximum. Allez-y, allez-y.
Merci. السلام عليكم ورحمة الله وبركاته. أولاً نشكر الأساتذة الكرام على قبولهم مناقشة رسالة شهادة الدكتوراه، كما نشكر الحضور الكريم على صبرهم الجميل على إن شاء الله هذه المناقشة. أستسمحكم بالبداية. As you see in the screen, the official title of our dissertation is Quantum Information in Spacetime. But the core of our research is an extension of quantum information into supersymmetric framework. And before we dive into specifically development of superqubit and superquantum algorithm, and before we dive into the data, let me give you an overview of the topics that we will cover today. Here's the table of contents of our presentation. We will start with introduction, where I give you an overview of the topics of the subject and its importance, and followed by the quantum, talking about the quantum computing or quantum information as emerged field from the information theory and quantum mechanics. And we're gonna explore the world of superqubit as minimal extended qubit to the world of supersymmetry. And we will see how we involve the superqubit in the world of computing, trying to find new algorithms to solve specific type of problems. And we will discuss the supersymmetric extension of Deutsch-Jozsa algorithm. And finally, we conclude our presentation by summarizing all the topics that I mentioned earlier, and also we will discuss about the future direction of this research. So let's start our introduction. As I said before, today we talk about new exciting area of computation that combines two scientific fields, quantum information and supersymmetry. And as we know, the quantum information marks transformative jump in our ability to process information and process information in a way that classical computer cannot match. And it's unlike classical computer, the quantum computer uses and exploits the weird and strange phenomena of quantum mechanics, such as entanglement, duality, superposition, and interferences. And this phenomena enable quantum system to perform calculations of profound computation and perform or process information in a way that classical computer cannot match. And before we go further, let me give you an example of quantum algorithm that showcase the supremacy of quantum information over the classical one. For example, the quantum teleportation, where quantum states are transmitted between two locations instantaneously without moving the real physical system. Another example that showcases the supremacy of quantum information is superdense coding, which enables the transmission of quantum state or more information by fewer qubits. And this algorithm showcases the supremacy of quantum and unique advantage of quantum information processing. And parallel to this quantum advancement, the concept of supersymmetry, commonly known as SUSY, has emerged from the fundamental particle physics as theoretical framework with significant implications. And we know that supersymmetry addresses to some advanced theory in physics, such as hierarchy problem associated with Higgs boson and the elusive nature of dark matter. And more importantly, it aims to unify the fundamental forces of nature in very high energy scale. And inside the core of this supersymmetry lies a very beautiful mathematical structure called graded D superalgebra. And this superalgebra enable or describe the transformations between two fundamentally different types of particles called bosons and fermions. And we have now, in one hand, we have quantum information, and the other hand, we have supersymmetry. So we can, in groundbreaking fusion of these two varied domains, the principles of supersymmetry have been extended to the quantum information science, and this has led to the creation of novel or new quantum information, a unit called superqubit. As we will see next, the superqubit is a fascinating mathematical object that incorporates both bosonic and fermionic components into single theoretical framework. And to push or to harness the computational power of this superqubit, we introduced it in our research. We introduced what we call supergates, which are unitary transformations or unitary operations that enable us to transform the superqubit from one initial state to final states. And with this supergates, we are able to construct more advanced quantum circuits that are capable of executing quantum algorithms, and that surpasses the capability of any quantum system. And this opens a new horizon for quantum computing and suggesting new pathways towards solving the specific type or towards solving problems that previously didn't intractable. And we focus about extending quantum algorithms, especially virtual algorithm, and its implementation in discrete quantum programming language. And moving now to the quantum information or quantum information concept. As I said before, the quantum information is emerged from the fusion of two varied domains, the information theory as platform and the supersymmetry, or quantum mechanics, which govern or which is the road of this field of computation. So we know that quantum information is governed by a set of postulates, starting from the first one, where any quantum system can be described by set by a vector state which encapsulates all the information about our system. Second postulate is describe the time evolution of our system, which is governed by Schrödinger equation, and quantum measurement, how we describe how we perform calculations or a measurement in a quantum system by replacing the measurable physical quantity by emission operator. And finally, how we obtain the quantum composite system by tensor product of this constituent. And we know that behind this quantum mechanics, we have some strange phenomena, such as superposition. Strange phenomena, when I said in the point of view of physics, but in the point of view of the information theory, is behind the power of the quantum information. And when we talk about superposition, which enables the quantum state to be or to exist in different states simultaneously, and this is enable us to open many branches of computations in parallel. And tunneling, where quantum system can overpass the potential barrier with no vanishing probability, duality where our quantum system can behave as wave and as a particle, and entanglement is behind the more powerful quantum information quantum algorithms such as teleportation and superposition encoding. And the entangled state happens when we have two parts of the system that cannot behave independently of the other, and the measurement of the first one affects immediately the second part of the system. And when we use or fuse this quantum phenomena with the format in the platform of information theory, so which describe this information theory, describe for us how we encode, how we process and transmit information, how we create information. In the fusion of these two varied domains, we obtain what we call a quantum information. And now, let me begin with more detailed introduction of the fundamental concept of quantum information. And as of quantum information, it's unlike classical bit. A classical computer or classical system can exist in state 0 and 1. And the quantum bit can exist in superposition of states. That means it can take the value 0 and 1 and all possible linear combination between 0 and 1. Mathematically, it can be described by a state vector or ket vector which is equal to alpha 0 plus beta 1, where 0 and 1 represent the computational basis of two-dimensional Hilbert space. And alpha and beta are complex numbers representing the probability amplitude of our system to exist in state 0 and 1 with the constraints that alpha squared plus beta squared is equal to 1 to satisfy the normalization condition. And we know that we cannot perform calculations only by one qubit, so our quantum system generalized to n qubit as follows. This is the whole system is described by this state vector. Vector is equal to E1 0, 0, 0. That means that E1 is probably the amplitude to obtain the system in this state where all the subsystems exist in state 0 and so on for the other, and always the normalization condition should be respected. And while this qubit is synthesis in this synthesis quantum system to represent the information, this framework extended to more high or high dimensional quantum unit called qubit, where qubit is can be represented physically by any tradable quantum system. Mathematically, it can be written as you see here, alpha 0 plus beta 1 is gamma 2, where 0, 1, and 2, the computational basis of our three-dimensional Hilbert space, with alpha, beta, gamma represent the probability amplitude of the last mentioned computing base. And extending further, the QD generalizes this idea to D-level quantum system, where D can be any integer greater than 2, and it can be represented as you see in this vector. And now the utilization of QD and Q-trees helps us to increase or enable increasing the Hilbert space exponentially and enable the encoding more information per quantum unit, and offers also unique advantages for quantum algorithm and error correction. And now to manipulate this qubit or to perform meaningful computation, we have gates which are just unitary operations designed to operate in changing the state of the qubit. And the simplest quantum gates is X gate, which play the role of the NOT gate in the classical computer. It enables the transformation of 0 to 1 and 1 to 0. And this Z gate can read the probability amplitude of one system. And the most important gate in this single qubit case is Hadamard gate, which enables the creation of superposition by transforming the state 1 and 0 to equal weight probability superpositions. And we have also moved into the multi-qubit gates, which are just gates that enable us to process more than one qubit at the same time. The most important one or useful one is a control gate, where the NOT gate is applied to the second qubit, which is called a target, by when the first qubit, which is called the trigger, if it is equal to 1, so the transformation applied to the second. This gate enables us to create not superposition entanglement of in our quantum system. It can be represented by matrices depending on the number of qubits that we apply. In this case, it's 2 to the power 2. Most important gates of multi-qubit gates is topology gates, which enable us to perform to apply the NOT gate for the third qubit when the first one and the second one is equal to 1. Otherwise, nothing happens. And we have now a quantum information unit, and we have gates to apply or to process this information. So we are able to construct quantum circuits that are capable of solving specific type of problems or different type of problems. For example, the most famous one protocol in quantum information is teleportation, where quantum systems are transmitted between two locations instantaneously without moving the real system itself. So this is a circuit showing how we can send unknown state from the sender to the receiver after applying some gates and measurement. The receiver, depending on the result of the measurement, it can perform a specific type of transformation to obtain the real qubit system. another type of algorithm that perform another type of calculations to solve specific other type of problems, like the Dessertation algorithm, which enable us to evaluate function whether it's constant or balanced, and a global algorithm which provide quadratic speed up of searching uncertain data. They solve different type of problems. Self-Shor's algorithm is also enable quantum computer to factor large integer exponentially faster than any non-classical algorithm. We have many types of quantum algorithms using a quantum information. And what is crucial here is that this quantum algorithm exploit only two quantum phenomena, the parallelism where multi-branches are created simultaneously via superposition, and quantum entanglement, which enable us to create no-local correlation in quantum physics, and this is very crucial in quantum computing. So, moving now to the central thing in our research is the superqubit. The superqubit, as I mentioned before, is what we call it a fascinating mathematical object that incorporates two components, bosonic and fermionic components, and we can describe it in the we have many definitions of the superqubit in the literature. We can say that this is a supervector element of unitary orthosymplectic group. We can say the minimal extension of the qubit to the supersymmetric framework, and mathematically it can be represented by the supervector equal to E1, 0, and E21, and E dot, where 0 and 1 are even computational basis of our grading space. And dot is representing the odd computational basis of our grading space. And E1, E2 are even Grassmann number, with E dot is odd Grassmann number, so all the vector or supervector is an even vector. And where E1, E2, and E dot are not just complex number, are Grassmann numbers. And if you want to know that the Grassmann number is a number subdivided into two parts, the body and the soul. Where the body represents any field number, in our case is a complex number, and the soul represents the multiplication of different number of Grassmann variables. And the Grassmann variables are anti-commuting variables. So we can also subdivide the Grassmann number into two parts, the even and the odd, where the even can be represented by any multiplication, even multiplication of the Grassmann variables multiplied by coefficient, and including the body, because the number of multiplication of Grassmann number is 0 in our case. And the odd part is obtained by multiplying the even number of Grassmann variables with coefficient. And it can be represented also in this way: 1 plus p squared over 2 theta sharp, alpha 0 minus beta 1, and alpha p theta beta p theta sharp, where p is just a parameter, and theta sharp is a dual conjugate of the theta and Grassmann number. And we can perform a calculation or meaningful computing by just one qubit. So we have many. We can obtain the composite system by tensor product of superqubits. In this, you can see here how we can obtain the composite system by tensor product if two single superqubit, where the coefficient E1, we have two kinds of coefficient of and odd, and already also for the computational basis we have an odd and even parts of our describing this our vector. Also we can obtain the three qubits by tensor product of the superqubits of the last superqubits. So also superentanglement is referred to phenomenon as quantum mechanics. In quantum information, we have a related quantum system that shows no locality. Also in superentanglement, we can obtain entangled states between two superqubits, and that means that if we have a composite system, we cannot mathematically decompose it into tensor product of its constituents. And this is in this vector show us the maximally entangled superqubits. The white qubits are manipulated by quantum gates, so our superqubit needs to be operated by using superqubits, or this natural extension of our gates. So the super gates can be represented by the super matrices. Super matrices that contain 4 blocks. We have 2 blocks, 2 even blocks, and 2 odd blocks. And we have the sign up. We can give this sign to the supermilitary transformation, and we can change the parameter to fit our need to build a meaningful computation of our circuits. And also, MITI superqubit gates are introduced in this research. So the natural extension of C0 and Toffoli gate. This is a conditional transformation algorithm. And also the Toffoli gate, which has, when we talk about the Toffoli gate, this is an extension of Toffoli gate, where we have two triggers and the target. We can perform different transformations depending on the trigger and trigger. Right. So we fuse, or we have a fusion of 3 by domain information theory and quantum mechanics, which gives us a race of quantum information. And when we mix it with supersymmetry, we obtain what we call a supersymmetric quantum information. And between all these fundamental operations of superqubit logic, we extend key quantum algorithm to supersymmetric framework by notably the super teleportation, which enable, which enhance or what we call extended the superqubit or superquantum teleportation by enabling the transfer of superqubit, which contain the bosonic and fermionic components via maximally entangled state and classical communication. So we, after applying this algorithm, apply some controlled super gates to entangle disentangled states, followed by measurement and feed-forward operations to reconstruct the original superqubit on the receiver side and preserving their supersymmetric feature, and show or demonstrates the feasibility of sending or transporting more richer quantum state through across distance. And also the other subtract or essential quantum, essential arithmetic and logic operations have been extended in this research by, and the other subtractor have been developed using superqubit, and it's enabled us to perform multiple computational at the same time or at the same output of the superqubit. And so we have the addition, and the addition part is carried out by the even part, and the subtraction in the odd part. So we have in the same input, in the same output, the same different result of logical operation like addition and subtraction. And also, that shows that algorithms have been developed or extended in this framework, but we are not going to talk too much because it makes part of more general algorithm called superprecise algorithm. And moving now to experimental and theoretical advances in superqubit and super algorithms. And when they say superqubit, experimental, we don't mean the hardware of this quantum computer, but just any implementation or execution of our algorithms in the Qiskit IBM quantum computer. And using Qiskit as quantum programming language and the IBM quantum computer, we simulate both standard and supersymmetric algorithms, where Qiskit is provided an open source framework that enable us to design, test, and run the algorithm or quantum algorithm in a simulator, and at the same time in the real hardware provided by IBM quantum computer. And by executing or implementing these algorithms, so we bridge the gap between the theoretical formulation, mathematical theoretical formulation of supertheory and the real world of operability using a quantum system. And this is the implementation in our, it's just a teleportation code in the Qiskit and the IBM. We follow just a series of steps, starting by importing necessary modules in Qiskit, creating a register, and in time the quantum states, preparing the quantum states that we need to send, and we can display the circuit and running the algorithm into simulator, and after that we can run it in the real IBM quantum computer. So moving now to the supersymmetric extension of the Dessertation algorithm, and let's begin with revisiting Dessertation algorithm, a milestone in quantum computing that clearly demonstrates the supremacy of quantum information. And the core problem it solves is determining whether a given Boolean function is constant or balanced. Constant when it gives us the same output for all the inputs, and balanced if it gives us 0 for exactly half the inputs and half for the other. And this you can see in the circuit. We have a register. We have a register of qubits initialized to 0 and 1 auxiliary qubit initialized to 1. And after applying the Hadamard gates, which enable us to create a superposition of all our computational bases, followed by oracle which encode our function, and final Hadamard gates to interpret the quantities. And this is the steps that we follow in this algorithm. And finally, we need to measure our our example of 3 qubits. So after the measurement, we can define only after 1 qubit if the function is constant or balanced. And by implementing this, we implemented this algorithm in Qiskit IBM quantum computer, which is designed to simulate quantum circuits for both theoretical and practical implementations. And this will become crucial when comparing the superqubit, supersymmetric qubit, and introduced later. And we start with importing the necessary modules and function in this. This is the code of the Dessertation algorithm, starting from the oracle implementation, setting parameter and execution, and then you visualize the circuit. And this is the result. This is just the Dessertation algorithm, not the extent one. And also we can write code to count the depth and gates count of gate counts of our circuit. And now, building on this foundation, our main research contribution is to extend supersymmetric quantum algorithm, including the Dessertation algorithm, which enable us to perform, in this case, to perform or to identify whether given function is two functions are constant or balanced. And this algorithm or this circuit started by setting up our quantum initial state by a set of the n qubit in the state 0 and 1 auxiliary qubit in the state 1, and after that we perform at the same time or in parallel way the Hadamard gate for the first register and super Hadamard gate for the auxiliary qubit to create superposition, whether in the superposition in the n qubit and the first n register and the auxiliary qubit. So translating this theory into practice, I implemented this superqubit into a Qiskit with adaptation of and simulation of the superqubit behavior. And in this circuit, the first qubit for the input superqubit, while we have some details like in this, we see in we will discuss later, because I think this is how we see the circuit of our Deutsch-User algorithm. It's just some parameters are changed in the Qiskit IBM quantum programming language to fit the superqubit and the implementation of the Deutsch-User algorithm. And comparing the standard and supersymmetric Deutsch-User algorithm, the supersymmetric version outperformed we can see that outperformed the conventional one in gates in terms of depth and gate counts, and in terms of, as I said, in terms of gates and efficiency. And even this promising field is, despite this promising theoretical result, this work has clear limitation. There is no hardware. There is no hardware or physical hardware that fits the superqubit and supergates, and all the implementations have been carried out by simulation and simulation environments such as Qiskit. And now the future research will need to explore the physical realization, perhaps leveraging or trying to find new techniques in quantum hardware. And also we are trying to extend the supersymmetric field to the other fundamental algorithms such as Grover's search algorithm and Shor's Grover algorithm and Shor's algorithm, trying to open new pathways to solve other problems of types of problems. To conclude, this dissertation establishes what we call supersymmetric quantum information and extending by introducing superqubits, supergates, and super algorithm, and extending the field of quantum computing. And through theoretical development and rigorous simulation and comparative analysis, we showcase the supremacy of super quantum information, including the super Deutsch-User algorithm. And this advances is not only deepen our understanding in quantum information through the lens of supersymmetry, but also going toward the new entirely computational paradigms enhanced our field. I'm deeply grateful for the jury, for my family, for my friends. Thank you for your attention.